Okay, so please have that sheet out right now. So that's just your rubric for the project. It tells you everything you need to have on your element poster. Okay. Along with this, I just want to remind you guys before we get started, before I forget. It's on. Yeah, it's good. Before I forget, periodic table 1 is due today. Okay, so please make sure you turn it into the Science Research Center sometime before you leave school today. So I'll probably right after this class. All right. If you take a look at the element poster project, basically what's going to happen is everybody's been assigned an element that you need to do a report on. Now, this sheet that you got here details everything that you need to have in that report. So I'm not going to go through every little piece of information on here. But the important thing is to notice that it's worth 30 lab points. So it's a pretty significant chunk of your grade. It should be, I say should be, relatively easy for you guys. And I mean, when I say easy, I mean it's still going to require work. But it should be relatively easy points to get because you know exactly right on here what you need to do in order to get all 30 of those points. So if you want to look at it, it outlines exactly how much every piece of it is worth. Okay? Now, if you're wondering what element you are assigned, first of all, Mr. Gussie's class, you should have all got yours on Monday. If you did not get yours from Mr. Gussie, you weren't here on Monday, you can't remember. If you look over here, he has his seating charts posted up there, and he has the element posters, like your atomic number, posted there. Okay? If you have myself or Mr. Blackford, if you go onto Canvas, there's a grade, it's under the grades, and it's called Element Poster Atomic Number. Okay? It's not going to count towards your grade, so it's marked as an ungraded thing, okay, but it's still under the grades right now. So if you go on there, you look, whatever score you have there, that's your atomic number. So if you have, I don't know, if you have 1, you have hydrogen. Okay, it doesn't mean you got 1 point and somebody else got 79 points. It just means that you have hydrogen, they have francium. Okay, so don't like freak out, think you need to get points for that. Okay, so just take a look, see what atomic number you have. Okay, so ultimately what we're going to do with these, we're going to arrange them like the periodic table up here. Okay, so what do you notice about this? The different families in different regions of the periodic table have different colors. You need to come stop by your tour's room and get that colored paper. Okay, I had a little bit different colors than Mr. Gussie had, so some of my colors are a little bit different than the ones on the sheet. Okay, so don't base this off. Like when you come to my room, I have all the paper laid out there, and it says exactly what atomic numbers go with which paper. So if you're wondering where you're at, you just take a look. Okay, I got atomic number, 11. Yeah, it's an alkali metal. I know it says red on here. Mine are actually on salmon paper for that one in my room. Okay, but I have a post-it note right on top of it. All right, so just check that out. If you have questions, ask me. Okay, or Mr. Blackford. Super. Okay, now I just want to show you guys something funny quick. Okay, please come and ask us for colored paper. Take a look at these two pieces of paper here, okay? They're both yellow, yes I get it. Does anybody notice what's going on with this guy over here? It's literally colored with colored pencil. Like, so don't be the kid that's like so scared to come talk to your chemistry teacher that you like spend all of your time on your element poster coloring your element poster the right color. Okay, so like, I'm not kidding. They shaded this whole thing with yellow colored pencil. And then they spent like probably like half that time finishing their rest of their poster. Okay, so please spend more time like on the actual content than you do on like something silly. That would be ideal. Okay, so just stop by some point. You can come by. Well, for me, you'll have to come by sometime tomorrow or I don't know, Friday. Okay, so just stop by the room and I'll give it to you. Stop by Mr. Blackford, Mr. Gussie, whatever. We'll have that for you. Okay. Yeah. Other things. If you notice on your rubric, you have a spot where it says there's a few items that should be larger and able to see easier than everything else. Okay, that is the name of your element, the 2-letter symbol, the atomic number, and the atomic mass. So when I say they should be larger, like if I'm standing here and they're on the wall over there, I should be able to see, yeah, that's copper, that's gold, that's hydrogen, that's helium, that's whatever. Okay, from this far away. Like now I don't need to see all the other little details that are on there, but I should see those things from a considerable distance away. Okay, so if you notice up here in the one on the board, like you would be able to read bromine, you'd be able to see Br, all those things from a distance away. Now, another thing, you cannot just go online and print off one big piece of all those, something that has all those all together already. So you can't go and print something that says bromine has Br, has the atomic mass, and has the atomic number. Like, we want you to design your own poster. So these need to come from separate spots. Does that make sense, everyone?
That will be easy to find, so we want you to show some creativity in how you put things together, rather than just copying what somebody else did and posted on the internet.
Yeah. Well, I would prefer that you do it with typed up stuff like this, because then it's neater. Yeah. Okay. All right. If you want to color, draw some things, that's okay too. But like, it should be very clean, neat, and nice, because we're gonna hang these things up in the classroom. Okay. So like, we're gonna hang this up for like the rest of the year in class. So we don't want to have like some trash, for lack of a better word, hanging on the back of the bathroom. I'm just saying. So don't be that guy, you know, just do a nice job, and then we can be proud of it when we hang it up in the classroom. Okay, was that or girls? Okay. Other things. You are going to have to, like, some of the stuff is going to require you to do research, right? Like, you're not going to be able to answer some of these questions without looking up some of this information. So you should and you need to include your sources on the back, just like this. Okay, and you can't just put one website in here, guys. It needs to come from more than one source. Like, you're probably not going to be able to find all this information in one place. So every single place that you go to, you need to include the URL right here. Okay, we're not asking you to go online and use, like, you know, online citation things, or try and do it all in MLA format and make this super intense. Like, literally just put the link to the site you use on the back. Okay, you can do it just like this here. So write them all or type them all out. Just send it to us. So it's as easy as copying and pasting those, so we know where you got your stuff from. I'm trying to think of anything else, Mr. Blackford. Did I miss
Make
anything?
sure that all of your information fits on the page.
Oh yeah, let's do another one. Yes, so everything needs to fit on this page. Like, yes, you think you're going to get cute and it's going to be fun. You're going to have little pop-out pictures that come off. Like, things are going to stick out the side. I don't know, whatever. Like, I've had kids do that before, okay? So, don't do that, okay? It needs to fit all on one sheet of paper. That's because these are going to get placed right next to other ones. So if you have information that's hanging over the side of your poster, it's obviously going to cover up something on somebody else's poster next to you. Okay, so you need to make sure that it all fits. It's nice and clean and neat. You don't have like loose things that are going to fall off. You don't like go nuts with like glitter or like confetti or something. So like when I put it up, I just get like a big shower on my face and like anything silly like that, okay? Clean, nice, neat, but creative. You do all those things. I have faith in you. Okay?
The examples that he's shown are, most of them have been cut out and they have little borders or whatever, so they're kind of literally cut and pasted onto the sheet of paper. They don't have to do that. You can generate this with
You could do the whole thing online if you make an online template or something. You could do that too. Okay, but your design. The point is that if you do that, you're designing the whole thing. So it's all your design stuff, not just copying and pasting. Okay, so this is one I think was probably done all on the computer, but you know, it's like they have a little border on there. They have some different pieces, so it's obviously shows some creativity. This one would be like obviously super creative. Okay, but it already breaks one rule. You can't have. So this is what I'm talking about. You cannot have all four of these pieces like in some copy and pasted thing together. The name, the symbol, the atomic number, and the atomic mass. Okay. This is another example here. Sodium. These are just different. I'm sorry. Before I get into that, does anybody have questions about like expectations here at all? Okay. I mean, it's all clearly outlined on the sheet. If you have any questions, come and ask one of us. Okay.
But please read the sheet before you come and ask us questions. Because if you ask us a question that is right there in black and white, you might get a little salty. A little sodium chloride.
You're laughing though. All right. So here's just some other examples of creative periodic tables. Here's one made out of pumpkins. I know it's a little bit past Halloween here, but I don't know. I'm just showing you these for fun. So this is one where they took and like scraped away the top of the pumpkin, so when they light it, it like glows from the inside. Here's another that we would, if you want to do this, periodic table cookies, we appreciate it. It's not going to help your grade, but it might make me in a good mood. You never know, like that might help somehow. I don't know, whatever. Last one, coolest one, a periodic table. So we got to get woods or something to make one of these. What are you laughing about? I don't get it. It's just a periodic table. It's good stuff. Okay, questions, comments, concerns? Perfect. Everyone's going to get 30 out of 30. I like it. Hopefully, anyways. Some of you probably won't. Mr. Blackburn is now going to talk to you about periodic trends. So you're going to need your other sheet that you picked up, your note sheet for the day. You can put that element poster sheet away.
If you don't have one of these sheets, please get hooked up. All right, ladies, gentlemen, let's giddy up. If you please look at your periodic trends note sheet. And I'll make one more announcement that Mr. Neubauer already made. Periodic table 1, the worksheet you got on Monday is due today. The due date on there says 11/29. It's not due 3.5 weeks from now. It is due today. So beyond that, today's focus should go fairly quickly. Can be done in half an hour, probably less than that, is periodicity. Periodicity is just a fancy, impressive, multi-syllable scientific word for periodic trends, or trends within the periodic table. We want to be able to make predictions within the periodic table. What happens to the different elements as you go down a family or across a period? Do they get bigger, do they get smaller, do they get more reactive, less reactive? All sorts of things. We got 5 different trends we're going to talk about today. You got 5 cute little periodic tables on your note-taking sheet. And in the middle of that note-taking sheet, you got this guy. That's where we're going to start. We're going to remind you of stuff we already know, and we're going to build on that. So, lithium, beryllium, sodium, and magnesium. That is just a puny little corner of the entire periodic table. But those 4 little elements in that corner are going to be representative of the behavior of the entire table. So we focus on those to begin with, and then we'll expand that to talk about the whole darn thing. Stuff you already know. Each period represents a new energy level. So the first period, period 1, has hydrogen and helium. Once we have those 2 electrons in that first energy level, it's full. And then we start with period 2, lithium, which has 3 electrons. Each atomic number on the periodic table increases sequentially because the atomic number tells us how many protons are in the nucleus. Each proton has a positive charge, and so our nuclear charge, or the amount of positive charge, is going to increase as you go across the periodic table. So starting with the easiest one, lithium has atomic number 3, which indicates it has 3 protons, each one with a positive charge. As we focus or discuss these, we're going to talk at least initially about neutral atoms, which means they're going to have equal numbers of protons and electrons. So this simple diagram is going to show us how those electrons fill their energy levels. As we said, the first energy level can hold 2 electrons. Once that energy level is filled, the next electron has to go in the outer track, or the next energy level. As a result, an atom of lithium, which has 2 layers or levels, is going to be bigger than helium or hydrogen, which only have 1 energy level. Beryllium has 4 protons. To be neutral, it's going to need 4 electrons. First 2 electrons fill that first energy level, then we start the second energy level, and we got room for 2 there. And from here, we could go to boron, carbon, nitrogen, oxygen, etc. Because we know in the second energy level, we not only have the s orbital, but we also have p orbitals. And when we did our little orbital shell diagrams, we had that, and then we went on. So we've got room for more, but we're just going to focus on this little corner for right now. So once we go to beryllium, we're going to come back to sodium. Sodium, atomic number 11. 11 protons, 11 positive charges in the nucleus. Having 11 protons in the nucleus does not significantly increase the size of the atom, because as we already discussed, when we talked about the different models of the atom, the protons are so puny compared to the relative size of the atom. It's like, again, putting a baseball in the middle of a football field. That's going to represent all the nucleus, whereas the rest of the football field and the stadium and the stands are the size of the atom, because the electrons are taking up so much space. What does take up the space are the different energy levels. So with sodium, our first energy level is filled with those 2 electrons. The second energy level is filled with the 2s2 and the 2p6. So we've got 8 electrons in that second energy level. And then finally, we need one more. We have to add that third energy level. Adding that third layer to the atom makes it, again, bigger. It's like Ralphie's little brother in Christmas Story. When he's getting bundled up, every time Mom puts another layer on him, he gets bigger and bigger and bigger, and he's waddling around like a red Michelin man. Magnesium, add another proton, makes no difference to the size. Whoop, so fast. Oh, snap. That makes none of us happy. There. So that's just a simple atomic model to help us discuss the trends, and we're going to start with the atomic radius. And as we've already kind of alluded to, each time we add an energy level, the size of the atom is going to get bigger. First of our trends deals with specifically that, the atomic radius. How big is the atom? We know that the radius is half the diameter of a circle. With atomic radius, we define it just a little bit different. It's half the distance between 2 nuclei of identical atoms. So whether these are 2 lithium atoms, 2 carbon atoms, 2 lead atoms, these are identical atoms, and we measure the distance between the two nuclei, we cut it in half. That is defined as the atomic radii. Sodium, bigger than lithium. Magnesium, bigger than beryllium, because we've got an additional layer on each of them. So as we go down the periodic table, they get bigger and bigger. So the atomic radius is going to increase as we go down. As we go across, something a little maybe unexpected happens. And they get smaller. That looks a little bit like a snowman, huh? That is the official atomic radius snowman of chemistry right there. That's what that is. And that shows you what? This, my dear, is the official atomic radius snowman of chemistry. So here's the arrow that you can draw. A big diagonal from bottom left to top right. As you go down and to the left, bigger. Just like the official atomic radius snowman of physics will illustrate for you. As we go across or up, we get smaller. Really big, really little. You don't have to add those circles if you don't want to, but if you like to draw circles, so far so good, that's easy. Yeah? Hydrogen? It's going to be pretty small, but it's going to be a little bit bigger than helium. The reason that hydrogen is a little bit bigger than helium, or that potassium is bigger than bromine, they both have the same energy level. So potassium has 4 levels, bromine has 4 levels. As we add more electrons and more protons, there's more charge. And so bromine, for example, with 35 protons and 35 electrons is going to squeeze just a little bit tighter than potassium with 19 protons and 19 electrons. And then when we get back across and go to rubidium, we have to add another level, and it goes and gets significantly bigger again. Okay, shielding effect. Before we talk about shielding effect, let's come over here and show you the picture that I drew.
Ladies and gentlemen, it's all we chatting here right now.
This guy in the middle.
If you're not paying attention, please stop bothering.
You recognize this guy immediately as a guy with a shotgun. He owns a kennel, and he wants to have that shotgun so that he can keep the intruders away when they come to try to steal his dogs. So he built himself a little spot right in the middle, and then he built a little kennel run for his dogs to run around in this fence, but it's a small fenced area, so he can really only put 2 dogs in there. His business got started to boom. So he wanted to add more dogs, had to add another fence. More dogs. How many dogs do you think I could fit in there? There's a bigger circle. Yeah. We could go 8 more dogs if we wanted to. So we got 2 dogs running around in here, 8 more dogs running around out here. If business really started to boom, we could add more dogs. What happens when you add more dogs? There's more barking, draws more attention, and then people start to sneak out from the woods. And they try to sneak over there and say, I want to get one of those dogs, because I want a dog. These dogs out here are going to be harder for the guy with the shotgun to see, because he's got 2 dogs running around here, 8 more dogs running around there, and who knows, maybe just 1 dog out here. But this dog out here is going to be hard to see because these 10 dogs are going to be running around kind of getting in the way. Get it? Maybe not yet, but that's shielding. Shielding. Don't worry, we're coming back to the kennel and the guy with the shotgun. Shielding is the reduction in attraction between the nucleus and the electrons that are on the outer energy levels. So the electrons that are out here are not as strongly attracted to the nucleus because, first of course, they're farther away, but significantly because there's 10 electrons that are zipping around inside, kind of getting in the way. And they make it harder for the nucleus to see, in quotation marks, see that electron. As a result, every time we add an energy level, the shielding increases, which means it's going to get harder and harder to see those outer electrons. So there's more and more shielding as we add more and more energy levels. As the shielding increases, the attraction decreases. I'm just saying that to reinforce what shielding is. So more shielding means less attractive force, which means that those electrons on the outside, if they were, say, dogs, would be easier to come and steal because they're harder to see, more vulnerable. Across the periodic table, possibly surprising, but I'll tell you why. Across the periodic table, the shielding is pretty much constant for a given period or for a given energy level. And that's because even though we're adding more electrons, they're all being added to the same energy level. So this electron is not going to get in the way of that electron. These 10 are going to equally get in the way of both of them. If we add another electron, these electrons that are in the same energy level don't get in the way, but the inner electrons do. So there's no additional shielding just because we're adding electrons to a given energy level. Just like over here, if we put another dog in here, this dog's not going to get in the way of this dog, just the dogs that are inside will get in the way of both of them. Moving on. Ionization energy.
We know that an ion is produced when electrons are either gained or lost. So neutral atoms have equal amounts of protons and electrons. If we lose or gain an electron, now we've got an ion. So ionization energy is a measure of how hard it is to steal or remove an electron from an atom. Very much like the kennelization energy is the amount of energy it takes to steal a dog from a kennel. So if you're going to steal a dog from this kennel, which one are you taking? This guy. Because he's the easiest one to get to. He's right there on the outer edge. And he's the farthest one from the guy with the shotgun. And you're going to be hardest to see when you got these other 10 dogs running around inside. And honestly, he's really going to be easy to steal if he's the only dog in that level or in that outer fence. At least if you got a second dog in here and you come try to sneak in here, they're both coming to get you. He's got reinforcements. But if he's the only one out there, it's just you and him. Easy. On the back of your sheet, your note-taking sheet, is a table with ionization energies. I'm going to revisit that in just a few minutes after we finish these other trends. But we'll talk quantitatively about ionization energies. So, as you might expect, the further you are from the guy with the shotgun, the easier it is to steal the dog. The closer you are to the guy with the shotgun, the closer you are to the middle of the kennel, the dicier it gets. So ionization energy over here is big. Ionization energy down here is puny. I'm ready if you're ready. You're ready. Okay, electron affinity. Previously we've talked about how much energy it takes to steal an electron. Now we're going to talk about how much energy is related to an atom gaining an electron. So it's similar, not quite the same, but similar. So the energy associated with gaining an extra electron the most stable elements are the noble gases, because they have full energy levels. They are happy campers. How many electrons would chlorine need to have a electron configuration of a noble gas? 1. If chlorine could pick up 1 electron, oh, so stable, so happy. What about sodium? How would sodium get to be stable? Have to pick up 7 or dump 1. So sodium is going to give that electron up very easily, as opposed to try and pick up 7 more. As a result, the electron affinity trend is the same trend as our ionization energy. Small tendencies to pick up electrons when you're over here. Big tendency to pick up electrons up there. Fluorine wants to pick up an electron so bad you don't even get it. Ready? This stuff makes so much sense, doesn't it? Yeah. Okay, electronegativity, that's our last one. Electronegativity deals with electrons in a bond. So when atoms bond together, they share electrons. Oops, I guess we don't need to close parentheses if we never opened them. So shared electrons are electrons in a bond. If we got two atoms that are identical, that are bonded together, say a chlorine atom and a chlorine atom, they both want those electrons just as badly as the other, so they're going to share them equally. That's because they have equal electronegativities. But if we've got sodium, which we just talked about, would be perfectly happy to pretty much dump that electron, versus chlorine, which would really, really like one to become stable. If they're sharing electrons, that chlorine is going to have the electrons very close, and the sodium is going to have those electrons far away. So if those are in a bond, those shared electrons are going to be way over by the chlorine, far from the sodium. And I don't know if this analogy works for you, but watching TV at home with your brother or your sister, you got one TV, you got one remote. Let's say that remote is like the pair of electrons, the shared electrons. One of you is probably more in charge of that remote or keeping that remote a little closer to you than the other. So whoever's kind of in charge of what channel you're going to watch and when you watch it, they're going to be the more electronegative of the two of you. Guess what? Same trend. These guys in the lower right, or sorry, lower left, really don't pull those electrons much at all. Up here, as I said, fluorine wants those electrons like nobody's business. Okay, so with that in mind, let's flip this guy over, talk about a few ionization energies. All right, on the back side, first thing I would like you to look at, we're so close to done, is valence electrons. You've got 4 elements listed below your valence electrons: sodium, magnesium, sulfur, and chlorine. Please take a moment to list or identify how many valence electrons you think each of those atoms or elements has. Remember that valence electrons are the outer electrons, outermost electrons. They are the electrons in the outer energy level. We got sodium and magnesium already diagrammed for you. What's the outermost energy level of sodium? It's energy level 3, and there's just 1. So sodium has 1 valence electron. Sodium happens to be in family 1 and has 1 valence electron. Magnesium. What family is magnesium in? Family 2. Guess how many valence electrons? 2. That's weird. It's not weird. What about aluminum? How many valence electrons would aluminum have? Good guess. 3. Because we've got 3s1, 3s2, 3p1, which is the third electron in the third energy level, which happens to be family 13, and then 14, 15, 16, etc., up to 18. Last digit. Last digit of the group number tells you how many valence electrons there are. That's pretty neat. So sulfur is going to have 6 in family 16, and chlorine in family 17 has 7 valence electrons. So we're simply going to talk quantitatively, specific numbers about stuff we just talked about a few minutes ago. Who really wants to pick up an electron? Chlorine does. Because if he got one more electron, he'd be full, stable, happy camper. If you look at chlorine, on that data table 6.2, the EI1, that's energy of ionization for the first electron, go across 1,251 units of energy to steal 1 electron from chlorine. Sodium only takes 496 units of energy to steal that electron. Relatively speaking, that's not very much energy. So sodium is going to give that electron, or let that electron be taken, much easier than chlorine. To the right there, 738, 1451, and 7733 are the 3 energies for magnesium. If you look at magnesium on that data table, E1, 738 units of energy. That's this guy right here. Doesn't matter whether we take the one on the right or on the left. But if we take this electron, 738 units of energy. That's easy. Anybody could do that. Once we take that electron, what's the charge on the ion? +1, because we took one of our negative charges away. So now the net charge is positive, which means we still have 11 negative charges floating around and a net positive charges, so those 11 remaining electrons are going to be even more attracted than they were before. Not a lot, but a little more attracted than they were before, which means taking the next electron, a little harder. That was 1,451 units of energy. Well, we could still do it. But now we got a +2 charge on this ion. We still have 10 remaining electrons that all have negative charges, so they're even more attracted than they were before. And we want to take another one. Not only are we fighting that positive charge on the ion, we got to go into the next energy level. So we got to hop that first fence and get in here to the next fence, and holy buckets. That's a big deal. How much energy? 7,733 units of energy. How does that compare to the previous one? That's like 5 times as much as it took for the previous one, which was about twice as much as the first one. So this was a significant jump from 700 to 1,400, But then to go from 1400 to 7700, whoo, buckets. That, when you see that big jump, that tells you that you have moved from the valence shell, the outer energy level, into the core electrons. And if you look at this data table, those shaded ones, you'll see that the top shaded one in each column is a huge jump from the previous one. So sodium, first one's easy. After that, you got to go into the second energy level. So it's a big jump from 400 to 4500. Magnesium, you get 2 easy ones, and then you get a big jump. Aluminum, 3 easy ones, and then a big jump. Chlorine, they really don't want any part of that, but they're all hard with chlorine. Okay, so that's ionization energies. One of the things you want to look for when we get into that a little deeper are those big jumps in ionization energies. That tells you when we're moving on to our core electrons. Here's homework. I'm going to give this to you. Hopefully I have time to do one of them, maybe 2 of them with you. Listen up, please. We've got 3 or 4 minutes. I want to do at least 1 or 2 of these with you. Due on Friday, 28 of them. All of them, there's no calculations. All you're doing is choosing one, circling one or the other. So for the first one, easy one. Largest atomic radius between lithium or potassium. It's going to be potassium, of course, because our atomic radius snowman of chemistry, we get bigger as we go down. Potassium is clearly below lithium, so if they're in the same family, all we need to do is find out which one is lower. Potassium. If they're in the same period, we need to find out which one is further to the left. So if you look at number 7, oxygen, carbon. Oxygen is there, carbon is there. So oxygen would be here, carbon would be here. Carbon is more left than oxygen, so carbon is going to be the bigger part of your snowman's nose. We talked about the trend for electron affinity. Make sure that you're reading carefully to identify whether we're looking for bigger or smaller electron affinities. So your electron affinities are going to be little down and to the left, big up and to the right. Numbers 17 through 27. 17 through 27 are ions. I need to remind you, or I want to remind you anyway, that ions are going to affect the size of the atom. As we lose electrons, positive gets bigger. That is not right. Positive gets smaller, negative gets bigger. And again, positive charges, if you got a positive ion, the electrons that are left are going to be more attracted because the electrons are all negative. They're going to be more attracted to a positive. So that's going to shrink the size of your ion. As your ion gets more and more negative, the repulsion of the extra electrons makes it bigger and bigger. Periodic table 1 due today.
Dragon Ball. What happened to Dragon Ball 8?
Jasia Stazik to the attendance office, please. Jasia Stazik to the attendance office.